Welcome, folks. It's my pleasure today to introduce Tamal Day, who will be speaking on computing generalized rank of persistence modules via unfolding to zigzag modules.
Okay, so thank you, Henry, and everyone in the committee to allow me to speak here. I thought I'll talk about a very recent result. Actually, I was working on it for a couple of years, but I think now it's ready to be presented. That's why I thought I'll give that talk. So this is about computing generalized rank of persistence modules. So I believe this will give an efficient algorithm. I'm not saying the efficient because maybe there could be more improvement, but at least it was not clear how to compute generalized rank for persistence module beyond 2-parameter persistence module. So this is a joint. Oh boy. Sorry. Okay, so this is a joint work with my former student Cheng Jin, and this is based on the paper on the archive I have loaded. Okay, so let me give you a little bit of background. So I'm assuming that P is a finite poset, first of all, and we all know what is an interval. It is a subposet of P, where I is convex with respect to the order. Which I'm denoting as less than equal to P, and I is connected. So that's what an interval is for me. A module is a functor, as we know, from the poset P to the category of, from the category of poset P and to the category of vector space, finite dimensional vector spaces in the field, say F. And an interval module, which I'll call it as a module whose support is an interval I, which I'm denoting as this math BBR with the superscript I, is an interval module. As we all know, it has all the vector spaces pointwise isomorphic to a copy of the field, and it is otherwise zero. And all the internal morphisms for the module, interval module, are identity. So it's basically the generalization of the interval module, as we know, even for 1-parameter persistence. Okay. So in this case, for example, I'm showing an example here. Here is a poset, the Hasse diagram of the poset I'm just drawing. And here are all the vector spaces. I'm just showing the vector spaces with some basis vectors. And these matrices, basically, I'm just assuming F to be 0, 1 or Z2. And these matrices gives the internal morphisms from this vector space to this vector space is given by this matrix here. So suppose I have a representation of a module like this. It is known that such a module can be decomposed into indecomposables. Indecomposable modules are the ones which cannot be decomposed any further. And in this case, for example, I have 3 indecomposable modules, like the 2 red ones, and here is a blue one. And this, it happens to be, in this case, these 3 indecomposables are interval modules, because every point has a unidimensional vector space, and all the maps are basically identity. And in this case, the 2 red ones are full interval module. It's a term I'm using. I call an interval module to be full if its support is the entire poset P. Okay. So we all know about this by this time in TDA that such a persistent module where the way I have defined, it admits a decomposition D and into indecomposable modules, and such a decomposition is unique up to isomorphism. And one thing I'll use here, not an isomorphism, but an equality, because I'm assuming that all these MIs are submodules of M. Okay, so that's why I'm using the equality here. And again, so a full, as I have already defined, a full interval module, I'll denote it as I, where the support is this entire poset P. So what we know is the following. For a two-parameter persistence module, suppose its poset is either, you can take it R2, but the way I was showing, you can also take it as the Z2 grid. So for such a two-parameter persistent module, we already know that there is this rank invariant concept by Carlson and Jamoudian. So basically what it does, given 2 points P and Q, which are comparable in this case, it maps this interval from P to Q to the rank of the map from P to Q, the internal map defined by the module, which is in the module. So this is well known, but suppose your interval is no more a rectangle. Suppose your interval is like this here, which is not a rectangle. Then the notion of usual rank is not well defined. You cannot just say I take a lowest point P and highest point Q and define the rank the way it is defined for the rectangle. So for this one, Kim and Memoli define what is called a generalized rank. And so this generalized rank, as the picture suggests, is actually, it is the rank of the map from limit to colimit. I'll not go into the definitions of limit and colimit because I'll not be using it, but I'll use a property of limit to colimit, and that should be enough for this talk. So basically, the generalized rank, the way I'm defining it is the rank of the module M is equal to rank of this limit to colimit map. Okay, so what was known, what we did in the past, like 2 years back, for a Z2 modules, a zigzag persistence can compute this generalized rank. For a two-dimensional module, in this case, like here, what we proved that you can take a zigzag path starting from on the boundary P1, and I'll not go over the details of how to compute a path, but from P1 to another point Q1 on the boundary of this interval, and you define a zigzag module on this path, and the number of full intervals, again, the number of red intervals in this case, will be exactly equal to the generalized rank. And that gives a very efficient algorithm to compute generalized rank for two-parameter persistent module. But the problem is that such a boundary you cannot define for beyond parameter 2. Okay. Say, for example, even in 3-parameter persistent module, I cannot define such a path. And that's the difficulty. And this is the thing which in this work we circumvent. Okay, so from now on, from limit to colimit rank, you can replace that definition with the following criteria. It is known by a result of Chamber and Lecher that the rank of a module M is equal to the number of full interval modules in a decomposition of M. So I already talked about the decomposition of the module M, and if you count the number of full interval modules, as I already talked about, the number of indecomposable which are in interval and whose support is the full poset P, that gives you the generalized rank. This is known. So the algorithm, the strategy will be to compute this number. All right, okay. So before I do that, I need certain notations. So what we call a zigzag module, I call a zigzag module MZZ, which is defined on the a zigzag poset PZZ. And what is PZZ? PZZ is a zigzag poset whose basically it's a sequence of zigzag arrows and which are connecting its point P0 to PM. And so here I'm just showing a zigzag module MZZ whose vector spaces I'll denote it as VPI, and the internal maps are phi I, which goes from VPI to VPI1 or VPI plus 1 to VPI, depending on this arrow, which direction it goes. So that's the zigzag module. Okay, now I'm going to define another concept, which I call as limit module. It's not a standard term. I just introduce it because the way I define it, it will be clear to you. I call a submodule of this MGZ a limit module if there is a limit representative for this module. What do I mean by this limit representative VP0 to VPM? It basically, what it says is a module created by the vector spaces pointwise, say VPI, which are unit dimensional. And the maps are isomorphic. Again, the maps are same as the identity. So in this case, this module, if you look at it as, this is the limit module because these are all unit dimensional vectors, like here. The only thing is that this should be a complete representative of the module I. And what it means that if some vector goes to 0, like this one here, then it has to be the sequence of segments of non-zero vectors must be interspersed with the zero vectors. Like at the end of the segment, the two arrows should go exactly outward, like this way and this way. Otherwise, you cannot match the vectors to the entire sequence. So in this case, I have shown these two sequences. One is here, another is here, which are interspersed by all the zero vectors here. And this is a limit module, I call. Okay. And sorry, this is the limit representative, and any module which has a limit representative, I'm calling it as limit module. Okay, and another notation I'll be using, B sub I is exactly equal to basically VPI. Okay, for a limit module I, a particular fixed representative, I'll denote it as a sequence of BPI P0 to BPI PM. These BPI P0 in this case are VPIs. Okay, because what I can do, I can choose any scalar in the field, and alpha times I is also the same module I, but its representative is this one. You just multiply every vector with the scalar alpha. That's also a valid representative for the same module I. Okay, and the first observation, which is a very trivial observation, if I have two limit modules, I and I prime, and two scalars, alpha and alpha prime in the field, the sequence of vectors where I sum the vectors pointwise, like here, I sum the vectors in the representative of I and I prime here. So I get a sequence of vectors again, and that's also a representative, limit representative of another limit module. Okay, so this gives me a way of summing two limit modules to another limit module. So this defines a pointwise sum, and the way the definition is, it becomes a valid interval module, which is the new limit module. One can see that the limit module is nothing but an element in the limit space of MG, actually. Okay, so what is the idea? The idea is, first I am going to unfold the actual module M to a zigzag module. So there is unfolding, I'll just define in a moment. So that becomes a zigzag module. Then compute in the zigzag module its interval decompositions. And once I have the interval decomposition, I look at what are the full interval modules in this unfolding, and try to see whether this full interval module I can fold back to a full module in the original module A. And the number of such full modules will give me the generalized, right? The main part is to figure out which of the full modules in the unfolded zigzag module can be folded back to the original full module in the original module name. That's what it is. That's the main challenge. Okay, so here is an example. So for example, here is a poset I'm showing, and here is a module. These are the basis of the vector spaces I'm showing, and these are the maps. So for example, this poset or this module, I can unfold it to a zigzag module here. The way I have done, I just traverse this way, came back to D, and then go to B. This is exactly, and I preserve the arrows. Okay, so this gives me an unfolding of this module to a zigzag module. And once I have this zigzag module, I basically copy all the vector spaces at the copied points. And also the maps are preserved on the arrows. And then once I have that, once I have a decomposition of the zigzag module, I try to see whether, for example, this full module can be folded back. They can be folded back only if at the copied points, like here D, another D, if the two vector spaces are exactly equal, then I can fold back. And in this case, it is, because this is V1 plus V2 and V1 plus V2. In this case, they are exactly equal. I can fold it back. So there is a full interval module on the original module M. So in this case, the rank will be 1. But here is an example where there is a full module, but I cannot fold it back, because this, at the copied points, the two vectors are not exactly equal. And in this case, actually, this module does not have any interval module as an indecomposable. So its rank is 0. But the point is, sometimes what can happen in the zigzag module computation, that your full interval module actually is not foldable, or you cannot fold it back, but maybe there are some adjustment of the representatives so that it becomes foldable. And figuring out when that happens is a main challenge. So I need to define what I mean by this unfolding. So unfolding of a poset is, so given a poset P, the unfolding, I call it as fold. So basically there is a surjection from the unfolded poset to the folded poset. That's the definition. And the surjection basically, here is the definition. But the surjection basically preserves all the orders. You go from unfolded to folded, it preserves all orders, and it should not introduce any new order. Okay, so in a sense, yes. So that's the definition of the folding S from the poset Q to P, but in the reverse direction, there's the unfolding from P to Q, and I call it fold SQ is the folding of Q to P under the surjection S, and its reverse is fold S inverse of P is equal to P. So in this case, you can see this DC, this arrow has been unfolded into two arrows here. Okay, all right. So corresponding to the unfolding of a poset, I also have an unfolding of a module. So in this case, now on the poset, the same poset which I considered, I have put a module. So basically all the vector spaces are assigned point-wise, and the linear maps are also given here. So here, the unfolding means you look into the unfolded poset and point-wise copy the vector spaces at the corresponding points. For example, the D will have the same vector space given by the vectors V1 and V2 as the basis. At both points D, here, same vector space will come. Okay, that's what this first condition. And of course, the internal maps also have to respect the internal maps here. Okay, so that's the unfolding of a module M. So here is a complete definition, and the unfolding of a module, the definition is exactly this. I'm unfolding first the poset, and corresponding to the poset unfolding, I'm unfolding also the module. You can think of it as a pullback from the module here to this poset here. All right. Okay, so now I have to define what do we mean by foldability of a module. Okay, so one notation I'll be using, if M1 and M2 are two summands of the module M, and then I'll sometimes denote M2 as the complement module of M1. M1 bar is M2. But remember, M1 bar is not necessarily unique. And there could be more than one which are complement of M1 actually. Okay, but the next definition where I define what is the foldability for a folding S, so of the poset Q to the fold S of Q, and the Q module N. So Q module N is here, Q module N. We say N is S foldable if for every copied points, the vector spaces are exactly equal. This is what it is saying. So in this case, it is foldable because we at the copied points, they're exactly equal. So I can fold it back to this one. Okay, under the folding S. So that's my foldability definition. And here is a bunch of properties of folding. I'll not go over this, but these are important properties which I use to prove why the algorithm works and everything is correct. So basically, it just tells you that if you have a decomposition here, if those decompositions satisfy certain criteria, that if you take it back here through the folding S, each one also become a summary, and vice versa. But then you have to satisfy certain conditions. Okay, I'll not go over this one, but these are pretty important theorem to be used to prove that everything is correct. Okay, now I'm going to introduce one more term called the complete module. So again, suppose I have an unfolding of a module M to MGG, or in the other way, I have MGG which folds back to M. Suppose I already have that. Then I say that an interval module I in the decomposition of MGG. So there is a decomposition of the zigzag module. I take an interval module in that decomposition because every module in the decomposition is an interval module for the zigzag module. We call it a S complete if and only the two condition happens. First, this has to be a full interval module I. Second, both I and its complement should be foldable. So I is foldable and its complement is also foldable. Then only I say this is a complete interval module in the decomposition of the zigzag module. Okay, and I denote kappa D is the number of its complete interval modules in the decomposition D. Okay, and we call D the decomposition, the zigzag decomposition is S complete if kappa D is equal to the rank of the original module. So our main task will be to bring this kappa D to be equal to RKM, basically to bring the zigzag module to an S complete zigzag module, or a decomposition of the zigzag module to an S complete decomposition. That's the main thing in the algorithm. Okay, so one thing one can prove the following, that suppose there is this unfolding of unfolding of M to a zigzag module MZZ, then an S complete decomposition of MZZ exists. So maybe the algorithm has computed a decomposition which is not S complete, but there is a decomposition. So it exists. So that means we should be able to compute it. Okay. And not only that, furthermore, any decomposition of the zigzag module, which is the unfolded module from M, satisfies the following property: the number of its complete modules in the decomposition D is always less than equal to the rank of the original module. Okay, and this basically follows almost from the definition. Let's see. So now, okay, this is a pretty important property again for the complete modules, to express it as the sum of limit modules. Here comes the importance of the limit module. Suppose the unfolded zigzag module has I1 through IL as a set of the limit modules. Certain modules will be limit modules. in the decomposition, because limit module has to satisfy its representative satisfies certain property. Not every internal module are limit module. For example, here, for example, this module, the two blue ones are not limit modules, because I cannot map something, because this arrow here is forward, I cannot map something to here. 0 does not map to this V1 plus V2 anymore. So these are not limit modules, but this one is limit module. Because, so in this case, actually, this is sorry, in this case, this is a limit module, but in this case, it is not a foldable module. In this case, this full module is a limit module, and it is foldable module. Okay, so this proposition says that every complete interval module, basically a complete module in any direct decomposition, d prime of this MGZ, satisfy the following property, that its representative can be expressed as a sum of representatives for limit modules in any decomposition D of MGZ. So this is a very important property which I use again to prove why the algorithm is correct. Okay, so now I'm going to define what is called convertibility, which I already hinted once. The convertibility basically alludes to the fact that certain full module here in the decomposition may not be foldable, but it can be converted to a limit module which is foldable by using the sums. So let's take this example here. So again, here is a module M which has been unfolded here, and this zigzag has two full modules, and there are two other intervals here which are not full. Okay, the open dots are basically it becomes 0. There is open dot means the vector is 0 there. Okay. Now, if you see that this red full module is not foldable because at the copied points D, the two vectors are not exactly equal. However, and neither is this one here, the blue one. Blue one itself actually is not a full module because its two endpoints, the vectors are 0, but it's a limit module, because the arrows are going outward, which are going to 0. So now what happens, I can add a limit module. Basically, whenever I say add a limit module to a full module, I mean add the representatives pointwise. So if I add this limit module to this full limit module red here, I get back this module here. Its representative now has changed because of this addition. But because of this addition, now this full limit module has become foldable. So that means now I can fold this one. And so now what I have done, my number kappa D, I have increased by this process. Previously here in this decomposition of the same zigzag module, my kappa D was 0, but here now kappa D is 1. And it turns out after this, I cannot do any further additions to make something else. In fact, in this case, there is no other full module to make it complete module. So in this case, I know at this point, the algorithm will determine the rank is 1. And here is the picture that the red module has been folded back to a full module in the original module M. And this blue one is basically is an interval module in the original one, but it's not a full module. Okay. So sorry, convertibility, yes. So here is a notation. I denote by tau D as the number of interval modules I in the decomposition D that are convertible, which I can convert by using the sum with the other limit modules, and I know its complement is foldable. That the number I call tau of D. And we can observe that the number complete module in the decomposition D has to be less than equal to the tau of D. By the definition of tau of D tells me this, that this number is less than equal to tau of D. Okay, now the one of the main proposition one can prove that the actual rank of the original module M is now sandwiched between these two numbers. The number of complete module in the decomposition now I have, and the number of modules which I can convert to complete modules. Remember, by definition of tau D, also the if already it is already complete module, it is also convertible module by the definition. So this rank is sandwiched between these two numbers. And what the algorithm does, it goes on increasing the number kappa D till it becomes exactly equal to tau D. And once that happens, I know that number has to be exactly equal to the rank of the original module because of this relation. Okay, and this is exactly what is happening. Here, my complete module kappa D in this case is 0, because none of the intervals in the decomposition is complete, so it is 0. But then it increases here by 1, so kappa D becomes 1, and that is exactly equal to, in this case, tau D. And so I know this is the rank right now. Okay, so the main theorem is the following, based on which we have the algorithm. So suppose MGZ is the unfolded zigzag module of a module M, and D be any of its decomposition. So D has been computed by some algorithm of the zigzag module. Now, if every convertible full module I in D, where the complement is also foldable, is S complete, if I know that, I check. This can be checked. If every convertible full module is S and its I bar is foldable, is S complete, then I know exactly that kappa D is equal to the rank, which I'm trying to compute. Because in this case, I know D is S complete. Otherwise, if the convertible full module is not yet S complete, then in that case, what I do, I convert the convertible module to an S complete module. So a convertible module, if I just convert it to a S complete module, and then in that case, that basically kappa D will increase by 1. And that's why the new module you get D prime, its kappa D will increase by 1, because I have converted a module which was not S complete, but now is S complete. Okay, and I go on, the algorithm goes on doing it. It determines which are the modules which are convertible, and then that's the one thing. And once it determines that it is convertible, it converts. So I get a new decomposition from the existing decomposition D to D prime. It goes on doing it till it cannot do any further. And that's the time I know that it has achieved the goal. And that's what the algorithm is actually. So the algorithm basically uses, first it unfolds. How to unfold a poset to a zigzag poset is just basically a graph traversal. You can always do an Euler path unfolding, and that's the way you unfold, and you copy the vector spaces. That's very important. And once you have that, then compute the zigzag decomposition, the interval decomposition of the zigzag module. And I use this annotation matrix because everything has to be done with the matrix operations in terms of the vector spaces. So basically, I compute the representative of the zigzag module of the intervals as the cycles. And those cycles, I convert them into the coordinates of a basis through this annotation matrix, which I'll not go into the details. And once I have that, then you can do this conversion. You determine if I is convertible and I bar is foldable, And mark I complete, update the decomposition, and just repeat the step 4, as I already explained. Again, I don't think I have the time to explain how the algorithm exactly does. It's a bunch of matrix reductions. It's persistence algorithm like reductions. Is basically it's solving a large system of linear equations. That's what it boils down to ultimately. Okay, so once you do that, again, I just do not have the time to go over that details, but it is there in the paper. And again, foldability of I-bar, again, you can see it there. One thing, so main result is now, once you compute all these things and from the algorithmic complexity viewpoint, if you analyze, this is the algorithm complexity you get. Suppose you have been given, so the algorithm operates on a filtration. I assume that the input is a simplicial P filtration. So on the poset P, I have the filtration of a simplicial complex. I assume that. And then suppose the P have size T, the poset size T, and suppose it is a filtration of a simplicial complex of size N. N is the number of simplices. Then the algorithm computes the rank of N in this time complexity, Tn. Basically, it's something like almost like a little more than quadratic, because here 2 plus omega is the matrix multiplication time, which is 2.373. So it will be a little more than quartic. So this is what you get for the time complexity of the algorithm. Here is one more thing, and then I'll stop. Here is a special case. Suppose you have the special case where your module is coming from the degree D homology. So you have a filtration and you have a D complex, meaning that the highest dimension in the complex K, which is being filtered by P, has the dimension D. And suppose we are considering the degree D homology, so that if you consider that module, for that case, now the computation becomes much easier, because because of these two propositions, you don't need to check convertibility and foldability. Basically, in particular, in this case, you just take the zigzag module MZZ and count the number of full intervals. That's enough. In this particular case, that will give you the rank. So what does it mean? In the case of graphs, so if you take the case of graphs, and if you are looking for the module induced by the H1, first homology, in that case, the rank, generalized rank computation is very easy. You just unfold the graph on a zigzag poset, or giving the zigzag module, and compute the number of full intervals there, like our 2-parameter persistence case. That will give you the generalized rank. So there is no need to go over the convertibility and foldability. And even for the so in this case, the time complexity actually improves. It becomes T to the power omega only, not omega plus 2, because I am not doing any conversions. And in the other case, and particularly for the graph case, actually the algorithm can be done in linear time. Okay, so it's so simple for H1 at least. For degree 1, you can compute the generalized rank in linear time. Okay, so that's what it is. I think my time is up, because I was told I should not be taking more than 40 minutes. And thank you very much. It is 40 minutes. So I stop here and open up for any questions.
All right, so before we get to questions, let's briefly unmute ourselves and applaud for Tamal.
Thank you.
So questions? Let me start first. You were explaining this complexity term. One of them had T omega n squared, I believe. And you were describing that as quartic or slightly above. That's because you're adding the omega and the
Yeah.
two each other.
Because I put with n is equal to order of t, this becomes t omega plus 2 because everything are clubbed together here.
I see. I see. So if the number of simplices is on the order of the size of your poset. Okay.
Mhm.
Further questions? So I wanted to ask a question. Now this was for an arbitrary poset, but as far as I understand, but you had a remark at the beginning how intervals in 2D are easier to work with than intervals in 3D. Could you say a little bit more about that and how your algorithm gets around that?
Meaning in 2D or in 3D?
Well, in this is an algorithm for 2D or 3D.
So the algorithm I present works for any finite, like the module supported on any finite poset. So which is more general than even the parameter poset. So
Right.
the parameter process is on Z to the D, but finite subset. Okay. So in 2D, let me just show you this one here. In 2D, we showed with Facundo and Kim is that if you take suppose this is the support of the module, like the interval here I, then if you consider a path on the boundary of the poset, okay, so this needs to be defined, but there is a well-defined notion of a path on the boundary, and if you now restrict your module only on that boundary. So basically for a filter, suppose the module is induced by the filtration, then what you will do, you will restrict the filtration only on this path, zigzag path. Now this will be a zigzag path. On the zigzag path, it will give you a zigzag module. Right? Because it will give you a zigzag filtration now. Because some of the arrows will, like in this case, maybe it will go up here, then to the left, then up, then to the right. So this will give you a zigzag path, and on the zigzag path, filtration will be a zigzag filtration. And there are very good algorithms now we have to compute the decomposition, the interval decomposition of a zigzag persistence module. So you just compute, and then the total number of full intervals in this decomposition gives you this rank. This is what we proved in. But now the problem. Think about it. Suppose you think about in. So in 3D. So in 3D, I have a three-dimensional interval. So what is the path now? Because this boundary somehow is two-dimensional now.
I see.
So you cannot now define a path. And if I cannot define a path, I cannot define a zigzag module because I do not have a zigzag filtration anymore.
So is it the case that you might try to find different paths, but those different paths might give you different answers?
Yes,
I see.
course. So you can always take a path on this two-dimensional boundary, but then, yes, I don't believe that, that there is any canonical path you can choose which will give you. Maybe that's another question, but I don't believe that is true actually.
Right.
Okay, so that's the problem. And so, for example, even here, like in this poset, this is not the two parameter. This is a poset. In this poset, how will you define a path here? Like, what is a path? I mean, you can take a path, like in this case, maybe this one. But if I have to include all the three, there is no path.
I see. I see. Yeah.
So that's why you somehow tear this entire thing into you linearize it. So I believe this unfolding thing is something is useful even for something else. I do not know yet, but it's very useful because if you think about it, after this unfolding, the entire information is preserved. I did not lose any information from the original module because I copied the vector spaces. And also I copied the morphism between the vector spaces.
Right.
So there is no loss of information. Only thing is, yes, somehow it has been linearized. So whatever you do with this linearized module, you have to interpret it properly in the original.
Mhm. Mhm. Yeah, no, I like your intuition that these unfoldings might be used for other things, right? They sort of remind me of covering spaces a little bit, although they're, certainly different.
Yes, no, this could be useful, but okay.
Further questions? Well, if not, let me end the recording here.